Hello, everyone. The theme of this paper is computation resilient to errors. The specific model of computation that we shall talk about is Boolean circuits, and the error model that we shall work with is short-circuit errors. I'm sure everyone in the audience knows about Boolean circuits. You have bits as input, and you can take nots, ands, and ors. So let me start by defining what is the short-circuit error. A short-circuit error affects gates in a Boolean circuit. And when a gate is affected by a short circuit error, or when a gate is short circuited, then the output of that gate is fixed to one of its inputs. For example, if you have a gate computing the AND of two inputs A and B, and it is short circuited to the input A, then the output of this gate is fixed to the value of A, regardless of what B is. So instead of computing the function A and B, it instead computes the function A. And therefore, we have an error. Now, short circuit errors are actually very common. I'm sure you have heard of the term even outside computer science. And therefore, one question that one can ask is, can we design Boolean circuits to be resilient to such errors? In other words, is it possible to take a Boolean circuit C and get an equivalent circuit C prime? C prime computes the same function as C. That is resilient to a constant fraction of short circuit errors. This means that if you take the circuit C prime and give it to an adversary, and the adversary can decide to corrupt or short circuit a constant fraction of the gates in the circuit, then you want the guarantee that regardless of how or where the adversary inserts its short circuit errors, the resulting circuits should still compute the same function as the circuit C. Okay, this is a great question, except that it has one technicality associated with it. And to understand this technicality, one needs to see what happens when you corrupt all the gates in a root to leaf path. So what you can do in a circuit is you can take its output gate, you can short circuit it to one of its children, then you can short circuit this child to one of its children, and on until you reach an input gate. And you only short circuited the gates on one path, so you only had a small number of errors, but you were able to fix the output of the circuit to one of its inputs. So by investing a small number of errors, you're able to make the circuit completely trivial. And this is a technicality that we want to avoid. So the right way to ask the question, and it's the way it has been asked throughout the literature, is can a circuit be made resilient to a constant fraction of short circuit errors on every root to leaf or output to input path? This means that now when you give the circuit to an adversary, the adversary is restricted to only corrupt a constant fraction of gates on every root to leaf path. And you want the same guarantee. You want that as long as the number of short circuits on any root to leaf path is less than a constant, you want the guarantee that the circuit C prime computes the same function as the circuit C. Okay, so this is the problem that we want to study. And let us see what is known about this problem. What is known, and this was first proved in KLR, is that if you restrict attention to the case when the circuit is a formula, so every gate has only one wire coming out of it, then you can make a formula to a resilient formula, which means it is resilient to a constant fraction of errors on every root to leaf path with only a constant depth overhead. So you can make it resilient by increasing its depth by at most a constant factor. Now, one thing that we know about formulas is that they can always be balanced. So the depth of a formula is logarithmic in the size or the number of gates in the formula. And a constant depth overhead also implies a polynomial size overhead. This means that when you take a formula and you make it resilient the way KLR do, you get a formula that is not too large. You get only a polynomially larger size, and this is great. But it only works for the restricted case of formulas. What do we know about general circuits? One thing that we can do is we can always take the circuit, expand it out to a formula. This keeps the depth intact, but may increase the size by an exponential. And we can apply the KLR transformation on this expanded formula. This will give me a resilient formula with, again, a constant depth overhead. But because we expanded it out into a formula, the size may be exponential in the size of the original circuit. So it also works for circuits, but you have to pay exponential in the size. And the question is, can we do better? Our main result is, yes, we can. And we show that it is possible to take any circuit C and to construct a resilient version of this circuit with a constant depth overhead, just like KLR, but only a quasi-polynomial size overhead. The size we shrink from exponential to quasi-polynomial, and this is our main result. Now, the first thing that one should ask is whether you can decrease it even further. Can you have an even smaller size overhead? And we conjecture that no, the best you can do is quasi-polynomial, but a formal proof of this conjecture will actually may be very hard, because even if you prove it in a non-existential, even if you prove it in an existential manner, it will imply that P/poly, which is the class of all polynomial size circuits, is not contained in NC1. And this is a long-standing open problem that we know it's very hard. The reason it will imply this P/poly not contained in NC1 result is because if you look at the contrapositive, if P/poly were contained in NC1, then any polynomial size circuit will have a polynomial size formula, and you can apply the result of KLR to get a polynomial size resilient formula, which would mean that the lower bound is not true. So if this is not true, then the lower bound is not true, which means that if the lower bound, to prove a lower bound, you necessarily have to show that P/poly is not an NC1. Okay, this is one story. The other story is by a slightly different analysis, we can actually get something really interesting, even for the formula case. What we can show is that if you start with a circuit that is actually a formula, then the resilient circuit that you construct using our transformation is actually really, really small in terms of size. The size of the circuit is almost s to the 1 plus epsilon, where s is the size of the original formula. So it's not even polynomial, it's close to linear. But the difference between this and KLR is that we actually construct a circuit, which is not guaranteed to be a formula, while they construct a formula. So they're both resilient, but this is a formula, this is a circuit. This has a polynomial overhead, while ours is close to linear if you start with a formula. Okay, so this is the summary of our paper. And for the rest of this talk, I will give you an overview of the proof of the main result, which is you start with the circuit C, and you want a resilient version of the circuit that is only quasi-polynomially larger in size and is resilient to a constant fraction of short circuit errors on every root to leaf path. The framework we adopt for this proof is actually borrowed from KLR, which used this framework to show that Boolean formulas can be made error resilient. What KLR want to do is they start with a Boolean formula, and they want to end with a resilient Boolean formula. And they do this by exploiting a connection between Boolean formulas and two-party communication protocols. Specifically, they use a result by Kashmir and Richardson that say that Boolean formulas are actually equivalent to two-party communication protocols. You have two parties, Alice and Bob, they exchange messages with one another, and they want to solve some computational task. And they show that, firstly, this equivalence also extends to the error resilient world. Error resilient formulas or short circuit resilient formulas are equivalent to resilient protocols where some of the bits sent by the parties may be corrupted. And once you have both these equivalences, you get that the task of constructing resilient formulas from Boolean formulas is the same as the task of constructing resilient protocols from communication protocols. And this is what they do. They construct such resilient protocols, it closes the loop, and you get resilient formulas from Boolean formulas. Okay, so this is the framework that we also adopt, but we start with something more general, which is Boolean circuits, and we want to end up with resilient circuits. Now, the first step in this framework was an equivalence between formulas and protocols. And now we are starting with something more general. So for sure, we also need something more general that we end with in this step. And actually such an object is known. You can generalize the KW transformation to circuits. And what you get is what we call DAT protocols with rectangular correctness. Now, I will define what these are exactly later, but all you need to know right now is DAT protocols are a generalization of communication protocols. And the specific DAT protocols that you get from this equivalence actually satisfy not only the standard correctness property, which we are all familiar with, but they satisfy a stronger rectangular correctness property that we shall see is key to this whole result. So we have this equivalence from this line of work that shows that Boolean circuits are equivalent to DAT protocols with the rectangular correctness. And what we show in the paper is the remaining two steps. We show that this equivalence also extends to the air resilient world, where we show that resilient circuits are equivalent to resilient DAT protocols with rectangular correctness. This is one step of the proof. The second step is to construct resilient DAT protocols from regular DAT protocols. And these are the two steps that together imply our main result. So as far as the first step goes, I will not be going over this step in the talk. It closely follows the ideas in this line of work that takes Boolean circuits to DAT protocols with rectangular correctness, but more complications arise because now you have errors. But the fundamental ideas more or less stay the same. And even for the second line of work, which is second step in the proof, which is constructing resilient DAT protocols from regular DAT protocols, I will show a simplified case. I will start with DAT protocols that have the strong rectangular correctness property, but I will only show how to get resilient DAT protocols with the standard Vector correctness property. So we will see this part of the proof. There's ideas needed to extend it to rectangular correctness, and then more ideas are needed to get all the way to resilient circuits. But this is what we shall see in this talk. Okay, so let us see what is a DAT protocol. The way I want you to think about DAT protocols is to look at it as a two-player pebble game over a directed acyclic graph. Imagine that you have a directed acyclic graph. It has a root node, which is where a pebble is initially, and it has some leaf nodes, which is where the pebble will ultimately land. Now, all the non-leaf nodes in this graph either belong to Alice or to Bob. All the Alice nodes I have colored blue, and all the Bob nodes are green. And these two parties together push the pebble along these edges so that it reaches a leaf. So initially the pebble is at the root. This is a blue node, it's owned by Alice. And therefore Alice can use her input to decide which of the children she should push the pebble to. Let's say she goes left. Now this left node is a Bob node. And again, Bob will use his input to decide which of the children of this node the pebble should go to next. Let's say he goes right. And again, this is an Alice node, and let's say it goes right again. So the pebble traces this red path from the root to one of the leaves, and this leaf is then associated with the output of this name. Crucial to this DAT protocol is the fact that when the pebble arrives at any given node, then the next step only is a function of this node itself. It is not determined, it does not affected by the path that the pebble took to arrive at this node. It is determined solely by the node the pebble is currently at. And another cool thing is that this notion of DAT protocols generalizes standard communication protocols in exactly the same way as circuits generalize Boolean formulas. Just as you can expand out a circuit into a tree and get a Boolean formula, you can also expand out such a DAT protocol into a whole tree, and you will actually end up with a communication protocol where the left and the right child of a given node corresponds to sending a 0 or a 1, and the path that is traced by the pebble will correspond to the transcript of the protocol. So DAT protocols generalize regular communication protocols, and we can also extend the error model from standard communication protocols to work with DAT protocols. Here, we can define an error model as follows. What you do is you have this whole DAT, and you give some of the nodes of this DAT to an adversary. And again, you have the restriction that the number of nodes controlled by the adversary on any root to leaf path is at most a constant fraction. Now, when the pebble reaches a node that is given by an adversary, let's say this one, then the next node that the pebble goes to is actually determined by the adversary, regardless of the inputs of the parties. So we know that Alice actually wanted this pebble to go right, but because this node is now controlled by an adversary, the pebble actually goes left and reaches this leaf. And therefore an error happened. So I defined DAT protocols. I defined the right error model for DAT protocols. And now let us see how to make DAT protocols resilient to errors. The way we do this is we note that DAT protocols are actually a generalization of communication protocols. And there are lots of known ways to make communication protocols resilient to errors. In fact, there's a whole field of study called interactive coding that deals with this problem, and a lot of work has been done on this. And the way we made DAT protocols error resilient is we take one of the approaches to make communication protocols error resilient, which is the rewind if error paradigm. And we generalize this to work with DAT protocols. So let us see what is this paradigm. The rewind if error paradigm actually captures a very simple idea of making protocols error resilient. Suppose you have a protocol that is maybe not error resilient, then the way to make it error resilient is to first just run this protocol for a few rounds. You just hope for the best and run it for a few rounds. Maybe there were errors, maybe there were not. But after you run it for a few rounds, you run a procedure that will try to detect if there were any errors or not. In standard communication protocols, this may be implemented by, for example, the parties taking the transcripts that they got, hashing them, and exchanging the hashes. Now, if the hashes match, then with high probability, there were no errors. And if the hashes do not match, then there was an error and you need to do something about it. So you run the protocol for a few rounds, you do this hashing trick to detect whether or not an error happened. And if you actually detect an error, then you rewind some of the rounds in order to fix the error. So now you know that you have a transcript that has some error somewhere. You delete the rounds you start deleting the rounds from the suffix, and eventually, hopefully, you'll get to a prefix that does not have any errors. So essentially what this paradigm says is, in order to make DAT protocols error resilient, we need to implement two subroutines. We need a subroutine that will tell us if an error happened, which is the detection subroutine. And then we need a subroutine that will help us rewind in case the detection subroutine says that an error happened. And we have both of these subroutines for communication protocols, but can they be generalized to general DAT protocols? Now, for the first subroutine, if you think about it, then you actually cannot generalize it, because in order to detect errors, what the parties need to do is to take their transcripts, hash it, and exchange these hashes. However, like we just said, in a DAT protocol, if the pebble is at a given node, then all the parties know is the current location of the pebble. They do not know the path the pebble took to get to this node, which means that they do not know their whole transcript. And because they do not know their transcript, they cannot hash it, and therefore they cannot detect errors. You could think about some other approaches like hashing only the current node, but those can be seen to not work. You actually need to hash the entire path, if you want to have correct detection of errors. So this is a problem. But suppose I told you that there is an article that tells you that an error happened or not. Can you at least rewind? And actually, for DAT protocols, even this is a challenge. For communication protocols, it was simple. You had the entire transcript, and if you want to rewind, you just delete some symbols from the transcript, and that's rewinding. But again, with DAT protocols, all you know is the current location of the pebble. You do not know the path or the transcript that led to this node. And because there may be multiple paths that go to the same node, you do not know which path to rewind on. So overall, all we needed was two subroutines. And unfortunately, we don't have either one. So, and actually there are serious issues with this. We actually do not know how to get either of these subroutines. And the only thing that comes to our rescue is that the DAT protocols that we start with, the protocols that we get from this equivalence, they actually not only satisfy standard correctness, but they also satisfy a stronger notion, which we call rectangular correctness. This stronger notion imposes some additional structure on the DAT protocols, and it is this structure that will help us make them resilient to noise. So let us see, what is this feature? What is rectangular correctness? Now, the actual definition of rectangular correctness is kind of technical, and it is hard to understand during a talk. So I will not define it, but I will tell you some intuition of how it actually works. So when we talk about correctness in the standard sense, what we mean is if Alice has an input X, Bob has an input Y, and with these inputs, the DAT protocol reaches a leaf L, then the output associated with L should be correct for X and Y. Now, rectangular correctness generalizes it, and it says that not only should this output be correct, but if two pairs of inputs, X, Y, and X prime, Y prime, reach the same leaf L, then the output associated with this leaf should be correct not only for xy and x prime y prime, but it should also be correct on the cross terms. It should be correct for the pair x y prime, and it should be correct for the pair x prime y, even if the leaf that is reached on these pairs is different from the current leaf that we're talking about. Okay, so this is the definition. It requires correctness on inputs that may not reach the leaf. But one question that you might ask here is, why does it matter? We are familiar with the fact that in communication protocols, the set of inputs that reach a given leaf is actually a rectangle. So if both xy and x prime y prime reach the same leaf, then xy prime and x prime y should also reach this leaf. So why am I saying that this is a stronger definition? The reason this is stronger is because for general DAT protocols, it is no longer true that the set of inputs that reach a given leaf form a rectangle. In fact, it could be an arbitrary shape. It could, for all we know, look like this weird L shape here, where the set of inputs that reach a given leaf, which we fix, is all the inputs in this green L shape. And now the difference becomes clear. Now standard correctness would only say that the leaf output is correct for this inputs in this solid green L shape, but rectangular correctness would also ensure that it is correct on all the cross terms. So it is correct on the entire rectangle that contains this L shape. And it may also be correct somewhere outside, but this is the bare minimum guarantee that rectangular correctness gives us. Okay, so this is a very brief intuition about rectangular correctness, and let us now see why it helps us detect errors. The reason it helps us detect errors is now that you have this entire rectangle for which you are correct, all you need to do is you have to check whether you lie in this rectangle or not. And this is actually easy, because if you are a rectangle, then all Alice needs to do is check if her input is on this X part of the rectangle, and all Bob needs to do is check if his input is on the Y part of this rectangle. If both of these checks pass, then the input is indeed in the rectangle and you don't need to rewind. And if one of these fails, then you do need to rewind, but you actually can detect that. So you're able to detect that you need to rewind, solving the first challenge. Now let's go to the second challenge. Now you're in a situation where you ran the protocol for some rounds. There was an error that you were able to detect, and now you have to rewind. How do you do this rewind? The way we do this is we adapt the meeting points approach from interactive coding. What this approach says is that when you're simulating a given round of the protocol, let's say round R, then you also remember your state from exponentially many meeting points on the path that you took to reach round R. So if you're at a given round R, this green circle, then you remember your state at round R minus 1. You remember it at R minus 2, R minus 4, R minus 8, and so on at exponential intervals. Overall, you'll remember log D points, because D is the depth of this tree or DAD. And you will rewind whenever you want to rewind to the closest point where your states were correct, where there were no errors. Okay. So this idea is simple, but the real question that you need to ask me is, why log D? Why can't I remember more meeting points? Why can't I remember all of them? And why can't I get away with fewer meeting points? Why do we need log D? The answer to this question is that, well, let us first see why can't you remember more meeting points. So the answer to the why can't you remember more meeting points is because, like I said, in a DAT protocol, all you really know is the current location of the pebble. You actually do not know anything about the path the pebble took to reach this node. So the way you implement this remembering of log D meeting points is by considering a new DAD, each of whose nodes is a log D length tuple of the nodes in the original DAD. So the number of nodes in this new DAD is actually the number of nodes in the original DAD to the power of log D, because each node is a log D length tuple, and that can appear as a new node. So the more meeting points you have to remember, the greater is the size of your new DAD, and the greater is the blow up in your transformation. And that's why we only try to remember as few as possible, and we remember log D. Now you got to ask me, why can't you get away with remembering fewer than log D meeting points? Why can't you get away with let's say constant many meeting points? And the answer to that is that we also want to ensure that no two meeting points are really far apart. And the reason is, suppose that these two meeting points here are very far apart, and the adversary inserts interruptions from this round onwards. So by inserting this small number of interruptions, The closest direct meeting point that you have is this one, which is really far. So you inserted a small number of eruptions, but now you have to rewind a lot. You have to rewind all the way to this meeting point. And because a lot of rewinds were made for very, very few eruptions, the protocol, the simulation will ultimately not be resilient. So you cannot remember more meeting points because you don't have, you don't want to increase the blow up by a lot. You cannot remember less meeting points because you want to be resilient overall. It hampers your correctness. And log D is what we remember. We think it's tight, and this is the whole argument. So this is how you fix the challenge of rewinding by remembering meeting points. I already told you how rectangular correctness gives you the detection oracle. And what you get is, if you have DAT protocols with rectangular correctness, I showed you how to construct resilient DAT protocols with a quasi-poly blowup with standard correctness. Now, you can build on these ideas and generalize them to get resilient protocols with rectangular correctness, which is a much stronger notion. And you can also generalize the line of work here to show that these resilient DAT protocols imply resilient circuits. So overall, you finish this loop and you get that you can get from Boolean circuits, resilient Boolean circuits with a quasi-poly overhead, which is the main result I claimed. So that's it. That's the talk. Thank you.